Welcome to the Persistent Programming in Real Life workshop. My name is Haris Volos. I am an assistant professor at the University of Cyprus. I have been working on and off on persistent memory for over a decade now, and some of my earlier work includes a system called Mnemosyne, which proposed lightweight persistent memory as an abstraction to byte-addressable non-volatile memory. Today, I'll be presenting joint work with Terence Kelly. Terence and I worked together at Hewlett-Packard Labs several years ago, and today we'll be describing our first collaboration since we left HP Labs. This talk is really all about stress testing complete hardware-software stacks against power failures. We have been doing it for years and will present our current best practices. The original motive for developing these techniques was to test various implementations of persistent memory, a term that we'll define and explain in detail in a little while. The techniques that we'll discuss, however, are equally applicable to testing conventional relational database management systems. Indeed, the methods we'll cover can be used to test a wide range of software that must withstand power failures. The main improvements in our techniques that have happened in recent years are that we can now perform more thorough and more strenuous power failure tests, and we can run the tests faster and at lower cost than in years past. Finally, the results we obtain with our current methods are more convincing. The companion to this talk is an article available from two sources. If you are an ACM member, you should have recently received the latest communications of the ACM by postal mail, assuming that the US Postal Service still exists. If not, you can get the CSM article from the ACM Digital Library. Otherwise, you can always download a free copy from the ACMQ magazine. The article cites a lot of earlier related work on testing persistent memory against power failures and also other papers that are important for anyone interested in this topic. It also tells you where to download the software that works with the test hardware we describe in this talk. Okay, let's get started. Protecting the integrity of application data is the highest duty of computing systems. Sudden failures of every kind are the main threat to application data integrity. Crashes due to bugs in applications and operating systems are major worries, but the worst threat is power failure. Think about what might happen if power fails while persistent application data is being updated. The data could be corrupted directly, or it could be effectively destroyed if its metadata are corrupted. If this sounds abstract or hypothetical to you, consider the concrete case of an application that transfers money from one bank account to another. An untimely crash could violate the conservation of money invariant by causing money to vanish into or appear from thin air. We cannot let that happen. Applications prevent crashes from harming data by updating data using mechanisms that are atomic with respect to failure. Such mechanisms promise to restore data to an application-defined consistent state following a crash, which will enable applications to recover. Examples of failure-atomic update mechanisms include AC transactions in relational database management systems, transaction key value stores, and new mechanisms for persistent memory. They all protect application data from power failures, or at least that's what the advertisements say. In practice, bitter experience has shown that many mechanisms that purport to update data atomically with respect to failure do not. We strongly recommend the following two papers, which are cited in the CSMQ article we mentioned at the beginning. One paper shows that, as of a few years ago, basically every relational database and key value store you have ever heard of does not implement atomic transactions correctly. They all lose data due to failures that they claim to tolerate. The other paper shows that, as of a few years ago, many solid-state drives lost data when power failed. Disappointments like this in mature commercial products that have been shipping to large numbers of paying customers for years cast doubt on all hardware and software tasked with keeping data safe, especially relatively new stuff. one will expect persistent memory to make persistence and resilience under failures a lot easier. However, as Steve Heller also points out in his last week's talk on planning to fail with reverse psychology, just having persistent memory does not solve the problem. Persistent memory software still has to worry about crash consistency, so skepticism is also warranted for that type of applications. Most of the defects in storage devices and failure-atomic update mechanisms are ultimately due to performance optimizations, which shouldn't surprise us because overzealous performance optimizations have been causing severe problems for many years. The man whose parachute does open is not the first to reach the ground. Unfortunately, the computer industry is full of people bent on making parachutes faster, and they often succeed. The most basic components of computers, including processors and main memory, have been profoundly defective due to performance optimizations going off the rails. You have heard of performance benchmarks for databases, right? Everybody knows about TPC. Can you name a single integrity benchmark or test suite? The industry's priorities are backwards with predictable results, broken artifacts that harm our data. If you're an application developer or operator and you truly care about protecting the integrity of your data, there is bad news and good news. The bad news, as we have seen, is that you cannot trust the software or hardware beneath your application. The good news is that you can test it. The right maxim for application developers and operators is train as you fight. Subject your entire hardware-software stack to the failures that it must tolerate in production. Today, we'll talk about testing the most menacing kind of failure, sudden whole system power interruptions. In the past, we have subjected our own artifacts to power failure tests. Please see the ACM article for details. However, we didn't thoroughly document the tribal knowledge required to conduct such tests. And that's what this talk is about. Of course, there is more to end-to-end reliability and assurance thereof than testing alone. Thoughtful design, careful implementation, and verification where possible are important links in the chain. This talk is about testing, which is not sufficient, but which is necessary. It's fine to test against less strenuous kinds of failures. Such tests are easier and faster than power cutoffs and may reveal bugs. However, gentler tests do not stress the system like sudden whole system power interruptions. Killing processes internally or externally is a kind of a crash, but it doesn't stress the OS or hardware. Shutting down the kernel in one way or another pulls the rug out from under an application, but it's an orderly shutdown even if it is done in haste and it doesn't stress the hardware. Some servers feature management interfaces that allow you to remotely power down the machine. This is much gentler and more orderly than a sudden power cutoff. Bottom line is that you should accept no substitutes. Test on genuine, sudden, whole system power interruptions. In the remainder of this talk, we'll describe a cheap yet effective power failure testbed that costs under $100, completes an off-on test cycle in a minute, which is 10,000 per week, and runs unattended indefinitely. Software developers should use this testbed or something like it to evaluate purportedly crash-tolerant software before releasing it for production use. We'll describe how we use the testbed to evaluate a failure-atomic update mechanism for persistent memory. We'll also describe our current work in progress that involves testing a well-known relational database. So, what do we want in a power failure testbed? Well, several things. It's important that a computer that is to endure power failures should be able to cut its own power. This allows us to trigger power failures whenever and wherever we please. For example, we can arrange for a power outage between every pair of semicolons in critical code. After power is shut off, it must somehow be restored, and the machine hosting the software and the test should reboot quickly and automatically so the next test cycle can begin. The host machine must be rugged enough to withstand many thousands of power-of-on test cycles. And finally, the overall testbed should be cheap for two reasons. First, we don't want anyone, even starving students, to have an excuse not to test against power failures. Second, successful tests on a cheap and flimsy testbed are more compelling than successful tests on fancy, expensive hardware. There are several candidates for the role of host computer in our power failure testbed. Most of them suffer serious drawbacks. Renting a server from a cloud provider doesn't work because by design, customer software cannot cut power to the bare metal. High-end servers are expensive and pose a dilemma. If you use their management interfaces to power the server, as we discussed earlier, that's gentler than a real power outage and might mask problems. If you subject a pricey server to real power cutoffs, you run the risk of frying. They are not designed to survive tens of thousands of power failures, and that's why the management interface for turning it off is gentle. It's easy to find throwaway laptops, but sadly, laptops lack BIOS features required to trigger an auto boot when AC power is restored following a power-off test. Workstations and PCs can be made to boot automatically when power is restored, but they boot slowly, and for large-scale testing, their bulk and power consumption are worrisome. So we learn about bad choices the hard way. Our previous power failure testbeds, which we used in at least 4 series of experiments described in research publications, were built around workstations. They boot so slowly that each power-off-on test took around 5 minutes. Another unfortunate feature of our earlier testbeds is that they used scriptable power strips. These power strips expose a network interface that allows a separate controller computer to cut and restore power to the host system under test. The power strips were fuzzy and poorly documented, and having a second controller computer is a bother. Worse yet, the host machine cannot easily cut its own power. A final unfortunate aspect of our early testbeds is that power is cut upstream of the host machine's power supply. It has been shown that the power supply contains enough residual energy to allow even a server-class machine to shut down somewhat gently rather than truly suddenly. The best host computer for a power failure testbed is a single board computer. We use the Raspberry Pi Model 3P Plus. They are cheap enough that anyone can afford one, and it's no big deal if testing destroys one. But testing does not destroy them. In our experience, they are quite rugged, especially considering the price. The Raspberry Pi runs Linux and nearly all Linux applications, so it doesn't restrict our choice of software excessively. It has the right instincts for our purposes. It boots quickly and automatically when power is restored after a power outage. It has general-purpose input-output pins, namely GPIO pins, that are designed to control external circuitry from a privileged software. And most importantly, the Pi is flimsy. If application software and middleware pass power failure tests on a Pi, the same software will likely pass similar tests on fancier hardware. Here is the basic idea for our latest PowerFail testbed. The host computer on the right is the only computer in the picture. Persistent application data lives in a USB-attached storage device hanging from the host. The host can cut its own power by sending a signal via its GPIO pins to the power interruption circuit in the center. The heart of the power interruption circuit is a tiny little electromechanical relay. Power from the power supply on the left runs through the relay's normally closed contacts until the interruption circuit cuts power by switching the relay's poles to the normally open contacts. We use a relay because it physically disconnects power, just like yanking a power cord with your arm. Note that power is cut downstream of the power supply. Residual energy in the power supply on the left cannot help the host computer on the right once the relay between them opens the wires. Our testbed is deliberately cheap and flimsy. If, say, a relational database passes Powerfail tests on our cheap hardware, it had done well better pass on enterprise-grade servers and storage, or the hardware vendors have a lot of explaining to do. For simplicity, we want to route the Pi's power directly through the relay's contacts, and we want the Pi's GPIO pins to control the relay's coil directly. We found exactly one double-pole, double-throw, DBTT, monostable non-latching relay that meets our requirements for the keystone of our power interruption circuit. The contacts must handle up to 2 amperes at 5.1 volts because that's what the Pi Model 3B Plus draws. The coil must operate at 3.3 volts and draw at most 60 milliamperes because that's all the Pi's GPIO pins can deliver. Please read the CSMQ article for the specs on this and all other components of our power interruption circuit. And yes, the relay makes a fabulous gig even. So Terence tried 3 different power interruption circuits for our Pi-based Powerfail testbed. The first was competent and it worked acceptably well, but in retrospect it was too complex and had too many components, so we are not going to show it to you. Its undersimplifications inspired the search for lean alternatives. The second circuit, which we'll see in a moment, was too simple. It doesn't allow us to control the duration of the power phase of each test cycle. The third circuit is just right. It has only 5 cheap elementary components, it works like a champ, and it allows us to control the length of time power is turned off before power is restored. Here is the circuit that is too simple. It is just a relay and the usual protection diode that we always place across a relay's coils. We route the Pi's power through the normally closed contacts, so when the coil isn't energized, the Pi receives power. 2 of the Pi's GPIO pins, under the control of software running on the Pi, can energize the relay's coil, which causes the contacts to jump away from their normally closed position, which cuts power to the Pi, which de-energizes the relay coil, which then allows the poles to snap back to their normally closed position, which finally restores power to the Pi. It turns out that the momentary power interruption caused by this circuit reliably triggers a reboot. But we are worried that the split-second power interruption we get from this circuit might mask failures that a more realistic, longer power outage will expose. So let's arrange for a longer power off interval whose duration we can control. Here is our preferred power interruption circuit, which we call PiNap because it causes our Pi to take a little nap. PiNap starts with the same relay and diode as the previous circuit and adds 2 capacitors, a resistor, and a few thoughtfully laid out wires. One capacitor helps the relay switch over to its normally open contacts. The other capacitor keeps the relay coil energized while the Pi is powered off. We control the time the Pi is off by the capacitance of C1. A larger capacitor means a longer nap. Our testbed cuts power for roughly 10 seconds. When the Pi is powered on normally, power from the power supply runs through the relay's normally closed contacts to charge both capacitors and power the Pi itself. Now we are seeing the transient situation as software on the Pi sets the GPIO pins to high, which energizes the relay's coil. The relay's poles jump away from the normally closed contacts and toward the normally open contacts. The Pi's normal power supply is now disconnected, so it cannot keep the coil energized. However, we cannot let the coil quit before the poles reach the normally open contacts, so capacitor C2 powers the Pi and therefore also the GPIO pins and the relay coil while the relay's poles are in flight, which is a millisecond or so. That's the trick that makes the PiNap circuit work, briefly powering the Pi with a capacitor while the relay's poles are in flight. When the relay's poles reach the normally open contacts, capacitor C1 discharges through the relay coil, keeping the relay poles at the normally open contacts and thereby keeping the Pi powered off until the energy in the capacitor is depleted. The capacitance of C1 and the resistance of the resistor together determine the duration of the power-off period. When C1 is spent, the relay coil de-energizes, the poles fall back to the normally closed contacts, and the Pi powers on and reboots, starting the next test cycle. A full power-off and test cycle takes 1 minute, including time for the software and the test to run for a while. That is 5 times faster than our old workstation-based testbeds, which took around 5 minutes for a test cycle. Here is the first prototype of the PiNap circuit on a breadboard. The relay is at the center, the big capacitor C1, the supercap, is the black rectangle on the top right, C2 is the cylinder on the right, the protection diode and resistor are adjacent to the relay. It's all very small and was fairly easy to assemble. Splicing the breadboard into the Pi's power cord involved some soldering, which was by far the biggest chore in building this prototype. And here is the complete prototype testbed on an 8.5 by 11 inch sheet of graph paper. From left to right, we see the wall-wart power supply, the power interruption circuit, and the Raspberry Pi Model 3B Plus with a USB thumb drive attached. Everything shown costs well under $100 and can be built in a few hours. Soldering breadboard-friendly wires into the power supply cord was the only time-consuming chore. The testbed is quiet and cool, drawing under 10 watts of power, and can run unattended indefinitely. Now, if you're going to build a PiNap testbed, here are a few tips. If you use an electrolytic capacitor for C1, it will be the size of a salt shaker, so go with a smaller supercap instead. Every component in PiNap, other than the resistor, is polarity sensitive, so be careful with polarity. Some of the Raspberry Pi's GPIO pins fluctuate between high and low voltage during boot. You need pins that remain low until you set them high. The ACM article cited at the beginning of the talk recommends specific GPIO pins and provides other tips for builders. Now, configuring the Pi and setting up the software to supervise tests involves details that we're going to skip in this talk. But the basic idea is to set up a cron job that runs when the Pi boots. The cron job starts a test application, the intended victim of the power failures, and then after waiting for a random interval, it triggers a power cutoff by signaling the power interruption circuit via GPIO pins. You also need to make sure that system logs and whatnot doesn't pile up with Unbound. A month-long test run once died because we weren't deleting logs aggressively enough. Please read the ACM article for the details, including where to download all the software you need to replicate our results or run different tests of your own. So we used our testbed to Powerfail test a recent implementation of persistent memory. I will explain what we mean by the term persistent memory, describe a few recent implementations, and then explain how we applied our Powerfail testbed to one of them. Nowadays, the term persistent memory is unfortunately sometimes used to refer to non-volatile memory hardware. In this talk, when we say persistent memory, we are referring to a software abstraction that can be implemented on conventional computers with ordinary DRAM and block storage. Newfangled non-volatile memory hardware is not required. If that sounds odd, the papers cited here explain everything. The basic trick for practicing the persistent memory style of programming on conventional hardware is simply to lay out data structures in a file-path memory mapping. It's easy and it can dramatically simplify software. No more serializers, parsers, databases, etc. Now, if your program must tolerate crashes, the right crash consistency mechanism for persistent memory programming on conventional hardware is failure-atomic msync, or FAMS. FAMS is one of those failure-atomic update mechanisms that we mentioned at the beginning of the talk. It protects data integrity from crashes by allowing programmers to evolve persistent data from one consistent state to the next atomically, even if crashes occur. So, is failure-atomic msync really failure-atomic? Does it really preserve data integrity from corruption by power failures? We used the PiNap Powerfail testbed to find out whether one very recent implementation of FAMS upholds its guarantees. Mnemosyne is a very simple user-space library implementation of failure-atomic msync that leverages a file cloning feature available in XFS and a few other file systems. To test whether the Mnemosyne implementation of failure-atomic msync protects application data from power failures, we wrote a very simple test application. The test application repeatedly fills memory with a very specific pseudo-random pattern and calls FAMS. As the program is running, we cut and restore power with PiNap and check whether the backing file containing persistent data has the expected pseudo-random pattern. We ran thousands of power-off-on tests on each of 3 different USB-attached storage devices: a cheap 64GB flash thumb drive, a medium-priced 500GB portable SSD, and a relatively expensive Hive 12GB flash memory stick. We ran over 58,000 power-off-on test cycles in total. All tests passed, not a single byte of data was corrupted or destroyed. From our test results, we cannot conclude that Mnemosyne and the software and hardware beneath it tolerate power failures. As Dijkstra famously noted, tests can prove the presence of bugs, but not their absence. All we can say is that our hardware-software stack is either fit for purpose as far as power failures are concerned, or maybe it's all just remarkably lucky. So Haris built the first PiNap testbed in California. I learned of this work after I took a faculty job in Europe and decided to build one of my own. I confirmed that the design works on a breadboard, then soldered a printed circuit board version. And here is the full testbed. And here is a close-up of my implementation of the PiNap circuit on a printed circuit board. It is much neater than the original breadboard prototype. Having now built the PiNap circuit, our goal is to use it to study the behavior of widely used database engines such as SQLite and MariaDB under power faults. We would like to find out whether these guardians of data uphold their transaction guarantees. Our testing methodology is to use the cron job to basically load the database with some initial known data, then run transaction workloads continuously to stress the database and trigger errors, and then after waiting a random interval, trigger a power off while running these workloads. We also plan to experiment with an alternative instrumentation-based method where we interpose on system calls and inject a fault with some delay in probability. Our thinking is that interposing on and injecting faults as system calls could expose more bugs than pure random testing because the power fault will happen closer to the error. But this is so far merely a hypothesis. We carefully craft the transaction workloads to stress the database engine under test and trigger errors. We start with implementing 2 single-threaded transaction workloads from Zeng et al. To trigger errors. The first workload updates multiple accounts with known values. This workload tests large transactions that update multiple rows and touch more than one block. The second workload moves money between accounts. This workload exercises multi-row consistency. At the end of each test cycle, we check that each transaction is all or nothing, which means 2 things. First, transactions committed before the fault are present, and those after are not. Second, consistency invariants continue to hold. For example, total amount of money stays the same. So I have an undergrad working on this project, and so far we have built and deployed one testbed based on a Raspberry Pi 3B Plus and the printed circuit board implementation of the PiNap circuit. Gradually, we want to build a few more to reach a total of 4 to 6 testbeds to parallelize and scale testing. The compact size, low power draw, low monetary cost, and rapid test cycle time of the PiNap testbed make it so easy to scale test that we have little reason not to. The student is currently implementing SQL queries for above workloads. After finishing the implementation of the 2 test workloads, the next step would be to test traditional system call-based engines, first SQLite and then MariaDB, and one Nmap-based engine such as LightningDB. To wrap up, we have seen that power failures pose the most serious danger to application data integrity. Failure-atomic update mechanisms protect data in theory, but they have disappointed us often in practice. Therefore, there is no substitute for thorough, realistic testing against sudden whole system power interruptions. Our PiNap power interruption circuit and a single board computer, like the Raspberry Pi, together make a versatile and powerful testbed that is cheap and rugged and capable of performing 10,000 of power-often test cycles per week. The famous Snap implementation of Failure-Atomic msync passed over 50,000 power failure tests, suggesting that it's not completely broken. Currently, we are implementing a couple of transactional workloads for testing the SQLite relational database. And finally, we are aware of several groups that plan to conduct realistic power failure tests involving obtained non-volatile memory, and we look forward to their results. Thank you for listening.